All right, so I'll start with just a little bit of an introduction of myself and my lab. So I'm from Spain in Europe. I was born in an island like Taiwan, but a little bit smaller. It's called Mallorca. Anybody know Mallorca? No? Nobody has been to Mallorca? Okay, that's fine. It's about a quarter of the size of Taiwan, something like that, maybe a little bit less, in the Mediterranean. I went to Barcelona at the age of 14 and studied something called telecommunications engineering there, signal processing, RF, antennas, all that kind of stuff. Then had the opportunity to do a dual degree with a university in Toulouse in France to study aerospace engineering as well. So that really changed my life. So I left Spain in 2002 for France to study, and I never came back. So I've been out of Spain now for about 23 years, I guess. I worked for Aerospace. So Ariane is the name of a rocket used by the Europeans. Maybe you've heard of it. They had Ariane 4, then Ariane 5, now Ariane 6 is coming. So I was an avionics specialist for the Ariane 5 program. I did 21 launch campaigns for Ariane 5. And then in 2008, I decided that I wanted to do something a little bit closer to design, conceptual design of space missions. So I decided to do a Ph.D. So I went to MIT in 2008, did my Ph.D. there for 4 years, and then a postdoc for another 2 years, and then I started as an assistant professor at Cornell University in New York, New York State, not New York City. And then in 2018, I went to Texas A&M, where I am now as an associate professor. So that's been kind of like a summary of my career. That SEEK lab thing, that's the name of my lab. It's called Systems Engineering, Autonomy, and Knowledge. We really work at that intersection of that Venn diagram right there. So a little bit small to see, but it says space systems, systems engineering, and artificial intelligence. And I really started right in the middle, in the intersection of these three, but I've been expanding kind of like to the rest of the Venn diagram, throughout my career. So you can see a picture of some of my students. It's starting to be a little bit old, that picture, but that's okay. We work on a number of topics related to AI, multi-agent coordination, global optimization, search algorithms, reasoning, knowledge representation. Lately, I've been doing a lot on this topic of how we can make Earth-observing systems more autonomous, more intelligent. So I'm going to be talking a lot about that. Let's see if that, there we go. Another topic that is, currently a source of funding for me is using AI agents of various kinds. It used to be called cognitive assistants, virtual assistants, digital assistants, AI assistants. Now we just call them AI agents. So these are basically agents that combine machine learning backends with a natural language interface. So now everybody's familiar with ChatGPT, of course. So the idea is that using a natural language interface, you can have a seamless interface, seamless information retrieval from various microservices, such as data mining, optimization, search, various things, anomaly, diagnosis, etc. So we've been doing a lot of that, particularly for this area of fault diagnostics. So if you're an astronaut and you're far away from the Earth, say on Mars or even beyond, in the future we're going to go to Mars, right? Communication delay is very long. It could be 20 to 40 minutes. So if you're trying to troubleshoot some kind of spacecraft emergency, let's say that CO2 concentration is going up in the cabin, oxygen is going down, you can't really have a conversation with mission control with that 40-minute communication delay, right? So you need some kind of AI support there that can help you figure out what's happening fast without relying on mission control for that. So we have a project right now that's been running for 6 years related to that. I've also had participation in a number of flight projects. So I was a member of the Constellation and Instrument Science team for the TROPICS mission, which is a constellation of CubeSats for tropical storm monitoring, which would be very relevant in Taiwan. Now I'm working on this other mission called Odin, which tries to demonstrate a new type of accelerometers for gravimetry to measure the Earth's gravity field very, very precisely. So we're basically now doing the early design reviews for that mission, trying to launch in a couple of years. All right, so with that, we're going to jump ahead into the topic of today's short course, which again, we're trying to talk about novel architectures, trends for these Earth observing systems. So let me start by going a little bit into the history, okay? So, and I'm going to have a little bit of a NASA and European-centric perspective here. I apologize if things are different over here, but generally speaking, we've been doing Earth observing satellites since, roughly the 1960s, something like that, right? And if you look at the kind of like the trend in terms of things like mass, for instance, the weight of satellites, you will see that the weight of satellites slowly went up, between the 1960s and the early 2000s. And it really peaked in the 2000s with very large missions like ENVISAT. ENVISAT is the largest civil Earth observing satellite ever built, about 8 metric tons, 10 instruments, 10 remote sensing instruments, big ones too, on the same satellite. So that was a European satellite. Then we had Terra, Aqua, Aura, the so-called NASA Earth observing system. So that's, again, from 1999 through 2004. So they were launched 3 to 5 metric tons, right? Terra was 5,190 kilograms. So that's very large, right? I mean, we're talking about a big bus, right? And, something that's huge. And lots of different instruments, radars, radiometers, spectrometers, limb sounders, right? So when you think about the engineering effort that goes into designing this spacecraft, very challenging, right? Because you have some instruments that are generating vibrations, things that are scanning, for instance, right? Other instruments that have to be very precise, controlled, right? Because, say, a limb sounder, if you have micro vibrations, it could be like a kilometer difference, right? In terms of where you're measuring, so you have to be really careful. So that creates essentially an engineering nightmare, right? So because of that, there was a reaction, and we tried to go back to smaller spacecraft and single instrument or fewer instrument kind of spacecraft, right? So that's when we started in the 2010s. We started having missions like Calypso, the NASA A-Train, for instance, where we're going back to 1 metric ton, class satellites, right? But roughly speaking, we've had this monolithic architecture dominating in the early 2000s and even a little bit beyond. So this means try to put a lot of instruments together on the same spacecraft, because you're going to get the synergies of the scientific measurements, right? They're looking at the same spot at the same time. So you can combine the data sets, cross-register the data sets, as that is called, and that's going to increase the science value of those observations, right? So from an operations standpoint, so today I'm structuring the talk in terms of first half is going to be design, second half is going to be operations, right? From the operations standpoint, by and large, up to pretty much now, the operation of Earth observing systems has been tremendously unsophisticated, right? So Earth observing satellites, basically, they look down all the time, and they take pictures, right? They take images of the Earth, they store them on board, wait to be in visibility of the next ground station, and when you have a contact, a downlink opportunity, dump all the data that you can, right? And that's it. There's no onboard data processing, very limited onboard data processing. Today, maybe, data compression, but in a lot of cases, the scientists don't want you to do that, right? They want the raw data because, you may lose information depending on the kind of data compression algorithm that you're using that you will never recover, right? So they don't want the automated system to do that for them, right? Maybe some cloud mask, it's starting to become more common. So that means, if you have a visible and near-infrared sensor, you're taking pictures and it's cloudy, you don't see anything, it's all white, right? So that image is pointless. You don't need to downlink it, right? So if you can do that, have a cloud detector essentially on board, you can decide to not downlink that image if it's too cloudy, right? But that's about it. That's the extent of onboard data processing that we do. No communication across satellites is very rare. For Earth observing systems, at least communication satellites, it's a different story, right? But for Earth observing systems, even if you have satellites in a constellation, they're not going to talk to one another. They don't share information they don't coordinate, right? So I call that a very static CONOPS, right? So with the early 2000s or 2010s, we had the CubeSat revolution, right? I understand you have a very active CubeSat program here that's starting with some of your professors working on CubeSat missions, right? CubeSats, small sats, that was a huge revolution, right? Because that miniaturization allowed to break a trade-off basically between coverage and spatial resolution, right? If you wanted continuous coverage, you have to be in GEO before, right? If you wanted good spatial resolution, you have to be in LEO, right? So now with a constellation of small satellites in LEO, you can have both. You can have very good revisit times, and at the same time, you can have very good spatial resolution, right? So that was a good revolution. Tropic, Cygnus, those are two examples of actual flight missions that NASA has flown that demonstrate constellations of really very small, in this case, actual CubeSat missions, right? And this is, we're talking about $30 to $100 million class kind of mission, which is much less than, that MVSAT, Terra, Aqua, Aura. MVSAT, 2 billion euros, right? Terra, Aqua, Aura, roughly $1 billion class missions, right? So this is an order of magnitude or more, less, right? We have Planet, used to be called Planet Labs, now it's just called Planet, with a constellation of lots of satellites, CubeSats, and now also small satellites that do high-resolution imagery, 3 to 5 meters, now adding multispectral capabilities as well, right? So the thing of these constellations is that they still have that, fairly static CONOPS, right? Planet allows you to actually do targeting of some of their satellites, so you can ask them to observe a certain ground point at a certain time. But all of that planning basically happens on the ground, right? It's not an onboard system, an onboard planning system that does that, reacting to real-time information, right? So I'm going to talk about how that creates some challenges. All right, so there you go. That's a challenges slide. What are some of these challenges, right? So one of the big things is that even with constellations of small satellites, we're still relatively limited in terms of the revisit time, right? So revisit time, that's basically if you look at a certain spot on the surface of the Earth, how often you're going to revisit that particular point, right? So of course, that's a time series, and it's not necessarily a constant, depending on the type of orbit that you have, but you can do statistics on it and calculate an average or a worst case or a 90th percentile, right? But roughly speaking, something like Landsat, which has been the typical satellite to do Earth observation work, we're talking about 2 weeks revisit time, right? Because the swath is very small. It's 180 kilometers, so that you can have a good spatial resolution, something like 30 meters, right? So it just takes a long time, to revisit a particular point on the surface of the Earth, right? With constellations and with instruments that have scanning capabilities, you can get down to maybe hours in the best of cases, days in most realistic cases, right? So that sounds like a very good thing, right? But when we're talking about, say, floods, tropical storms, this typhoon alert that we had yesterday, right? And we didn't know what was going to happen, right? So in Texas, where I live, floods are extremely common, right? Because the soil doesn't take any water. So when it rains, it floods. So we had what is called flash floods, right? So with almost no time, in something like 30 minutes, it goes from perfectly dry to streets flooding and cars floating on the streets, essentially. I'm exaggerating a little bit, but you get the point, right? So we really need to improve our response time from a societal perspective, to improve our response to these disasters like floods, fires, and other things. I've been working on more exotic things like algal blooms, when you're on a lake and all of a sudden, on a space of a few hours, it goes from blue to green, because there's a sudden increase in chlorophyll concentration and algae just bloom very fast, right? That's called an algal bloom. So either way, we need to improve our response time and also improve our spatial temporal really sampling of these, let's call them events of interest. That's what we call them in our project, which again could be floods, fires, algal blooms, or even, if you think, obviously this has military applications as well, right? An event of interest, I don't need to tell you, it could be things like, a launch of a certain, missile or something like that, right? So there's current research and development related to these topics. There's something called intelligent pointing, which is related to dynamic targeting. That's really the state of the art in terms of what's starting to be demonstrated in some demonstration missions. So this is the idea of having actually some onboard data processing of the data, that the images that you're gathering, and being able to determine the presence of some of these events of interest, and in real time adjust your plan, your operational plan, to be able to point your instrument to observe these events of interest more often or faster, right? So that's called intelligent pointing. We've done some of this work in my lab. There's other labs that have done some of that, right? It's been used, again, this is still R&D, right? In some cases, this has not been flown. This is all at the level of simulation, right? So early TRL. But it's been used, say, for soil moisture, right? You want to know how much water is in the soil, right? So instead of just having a static ConOps where you're just looking down with a fixed pattern, always looking at the same spot, what you can do is in real time, do the soil moisture retrieval. And then based on, with that retrieval, what is the expected, current best estimate of the soil moisture in the point, there's an error bar also that comes with that, right? This is, 10% soil moisture or 30% soil moisture plus minus 10%, right? What you can do is that you can target areas where that error bar is larger so that that uncertainty can be reduced, right? So that's one criteria that you could use to guide the operations. There's many other criteria that you could imagine, right? Maybe you want to target points where it's raining, so you think that soil moisture is going to change very fast in those points, right? Or points where it's about to rain, for instance. It's been used for snow detection as well, and it's been used also for this dynamic targeting idea. So the idea of this is that you have an instrument that's called a look-ahead instrument. So it's an instrument that instead of looking down, it's looking ahead in the orbit. And what it's doing is providing a little bit of, depending on what's this angle, a little bit of lead time to do the onboard data processing, right? And decide where you want to point with the main instrument, which is looking down, if that makes sense, right? So that's called dynamic targeting. It's starting to be demonstrated right now for various things like storm chasing or things like planetary boundary layer, when you're looking at the very bottom of the atmosphere, which is hard to measure because you have the rest of the atmosphere, in between, right? So that's some of the stuff that has been demonstrated. What is the future? What is what we're envisioning would happen in, say, 10, 20, 30 years? We've been saying that, by the way, for about 10, 20, or 30 years, right? And, it's not quite there yet, but it will come. Earth observing sensor webs, right? This is a relatively old concept, 30-year-old concept, where I think it's well illustrated with this picture from NASA. You have various satellites, UAVs of various sorts, and ground sensors, all doing onboard data processing in real time, talking to one another, coordinating operations in an autonomous fashion, right? All to improve that spatiotemporal sampling, to improve that response time for the events of interest, right? So this is what I'm going to talk about today from a design standpoint and from an operations standpoint. All right, so I'm going to stop here for a second and see if there are any questions before I get into the design stuff. So I don't know if you guys have had any courses on systems engineering, system architecture. This will be a crash course, 5-10-minute course on system architecture, okay? So the warning here is that if you're an engineer, like most engineers, you're a very practical person, right? So systems architecture can get a little bit abstract, almost philosophical. So if you're lost for a second, bear with me, feel free to ask questions. I will try to make these as digestible, palatable as possible, right? So two key words in system architecture are function and form. Function is just what the system does, okay? The functions of the system, right? So for an Earth observing system, the primary function is to take measurements of stuff, right? Take images, take observations, right? For the car, your main function of the car is to take you from point A to point B, is transportation, right? Form. Form is what the system is, what the system looks like. So form is what bears the cost. Function is pure value, right? Form is the cost that comes with that, the components, right? Including the software, right? Hardware and software. So if you want to measure soil moisture, the related element of form, you have various choices, and that's where architecture really comes into play, is in choosing what form is going to do what function, right? I can do it with an L-band aperture synthesis radiometer, like the Europeans did with the SMOS mission. I can do it with an L-band SAR combined with an L-band radiometer, like the Americans did with the SMAP mission. There's various elements of forms, radars, radiometers, essentially instruments, right? So the main elements of form of space missions for Earth observation are remote sensing instruments, spacecraft, rockets, and I guess orbits, if we can call that, form, right? All right. Concept is the mapping of function to form. Again, which forms are going to do which functions. And it's really at the highest level, right? So when I say something like the concept of the SMAP mission, that's a NASA mission, soil moisture active passive, is to measure, provide high resolution measurements of soil moisture, that's the function part, right? Using a combination of an L-band SAR and radiometer that share the same dish. That's the form part, right? That's the concept. And what architecture is taking the concept and starting to decompose it. You decompose the function into different levels of function, level 1 decomposition, level 2 decomposition, and for the same thing for form, right? So, okay, I need to measure soil moisture, but what do I really need to do that? Well, I need to collect radiance in a certain band. Probably I need to filter it. I need to amplify signals, right? I need to communicate, right? I need to store data. I also need a lot of supporting functions, provide electrical power to the sensors and so forth, right? So that's the system architecture functional decomposition, and the same thing for the form, right? If you have a spacecraft, it's divided into subsystems. Subsystems are divided into components and so forth. All right. That's one view of system architecture, is the function to form mapping, right? Another view is if you think about architecture as the most important design decisions that you're going to make. Okay, so you can think about it as the top 10 design decisions that will really define the system, all right? When we're designing a system, we always have decisions to make, right? When you're designing a house, right? What will be the system architecture of the house? Well, first, location, probably. In real estate, location is probably the most important thing, which drives most of the cost, right? If it's a more desirable location, right? Then maybe the house type or style, right? Maybe how many floors, how many bedrooms, bathrooms, that's the big stuff, right? Once you have decided on that stuff, the rest is detailed design. Once you have made your architecture decisions, roughly about 70% of the cost of the system is committed. You haven't spent anything almost, right? Whatever it took you to do the analysis to make the architecture decisions, but you have already committed most of the life cycle cost of the system. That's the idea about architecture decisions. You can see here, this is the percentage commitment of life cycle cost as a function of time. And you can see that, by the time 20% of the time has been spent on a project, which is again the system architecture stage more or less, you have already committed about 70% of that life cycle cost. So some people call it, architecture is the DNA of the system because it, kind of defines everything else, right? We gave the house example. All right, that's good. So what is the architecture of Earth observing systems? Well, we already said the main function, there's lots of functions, but the main function is to provide those measurements, right? That's the function that delivers value to the stakeholders, right? The form, the instruments, and really the orbits. And of course, there's spacecraft, right? But in a sense, I'd like to say that if you give me an instrument and you give me an orbit, designing the spacecraft is kind of like an exercise for the reader kind of thing, right? It's really design, right? Once you decide which instruments together in which orbits, that really is the architecture of the mission for the most part. We have our concept example for the soil moisture mission. Key architectural decisions. So what is that drives most of the cost? Well, there's the requirement side of things, right? We tend to think that requirements are fixed and given, but when you're designing a mission from scratch, requirements are far from set, right? There's this back and forth between scientists and engineers, right, about what is doable, what is feasible, and what is desirable, right? So setting on those requirements, do we need 100-meter spatial resolution, or can we live with 250, right? So that's definitely part of the architecture. And then the instruments, of course, and the orbits. So if you try to turn this into a mathematical problem, okay, you could think about an instrument selection problem. You have a set of possible instruments, and you have to choose a subset of those. Anybody familiar with combinatorial optimization may recognize a knapsack problem here, if you're familiar with that term. I'll talk about that in a second. This one is more, okay, so let's say that you've selected these instruments and not selected these instruments. Now you have to allocate them to orbits and to spacecraft, right? So there's an instrument to orbit or instrument to spacecraft allocation problem. That sounds like an assignment problem, a transportation problem. There's lots of problems in combinatorial optimization that are similar to this. You have two sets of entities and you need to form what is called a binary relation between these two sets. All right. Okay, so that was a quick primer. So hopefully that gives you a little bit of context, right? And now I'm going to talk about two topics, evaluating architecture. So how do we know if an architecture is good or bad, or if it's better than another architecture? And then this idea of tradespace exploration. So this is basically using that mathematical formulation of the problem to try to use computers to help you make these decisions, okay? So let's see, time-wise, where do I have the time? 34. So do I have like 15 more minutes or so before we need to break? What do you guys think? Okay. All right, so let's go into evaluating architectures. So if you go to theory of system architecture, it will tell you that an architecture is good if it satisfies the needs of their stakeholders. That's not very useful, right? It's not very concrete, but it's actually quite useful. So you have to think about who is the mission delivering value to, right? And what do these people want, right? So you have, let's say this is for NASA, right? But you can imagine that a chart similar to this exists for Taiwan, and you guys could probably make it much better than I can make it, right? But of course, it's a NASA mission, so NASA has to be somewhere in there, or NOAA if it's a weather mission. And these missions are funded by the government, of course, so the government has to be there, Congress, who funds NASA, right? A lot of turmoil right now with Congress not funding NASA at the appropriate levels and things like that, right? So it's definitely a very important stakeholder, right? But look at all these other boxes here, right? Obviously the scientists, those are the primary users, the primary ingestors of the data, right? The missions are providing data so the scientists can do science, right? And advance our understanding of the Earth system, right? But there's also commercial industry, commercial data users, the public, right? I mean, think about society as a whole. Not only are we funding the government through taxes, which funds NASA, right? We're also voting the government in, right? We're providing feedback to the government by doing things like demonstrations when the government does something that we don't like, right? All of that creates indirect value loops in this stakeholder value network. This is what it's called, right? So people have actually attempted to quantify these value loops in order to basically get insights into when you're designing a mission, should you prioritize, say, climate community requirements versus weather forecasting community requirements, right? Okay. All right. So that's all good, right? But if we're trying to become more concrete, let's focus on a more narrow thing, right? So let's focus on scientists, the users of the data, right? What do these users want? They want data products of various kinds, and they want data products that essentially meet some requirements instead of, in terms of a number of attributes, right? So it has to have enough spatial resolution, it has to have enough accuracy, It has to have enough revisit time, right? So those attributes of these data products is what really defines the performance of the system, right? So you have here spatial coverage, sampling, and resolution. Those are all different concepts, but related to essentially, how much data are you providing spatially? Same thing for spectral. You have spectral coverage, what is the different spectral bands that are covered, different from spectral sampling and resolution, right? How many bands do you have? And when you're measuring at 432 nanometers, is it really 432 nanometers or is it 435, right? That's the resolution piece. Temporal coverage, sampling, resolution, radiometric, right? So the accuracy side of things. And then latency, right? If you think about what this is telling us, it's basically telling us, I want a lot of data, I want good data, and I want it now, right? Those are the three dimensions of the value of a data product, right? Latency, by the way, is just the time between data acquisition and the time where the data is available for the user, which in some cases is surprisingly long, right? Even if the data is, downloaded in a matter of, in some cases, minutes, right? It takes a long time to process that data and make it available to the users, right? Now the near real-time paradigm is becoming more common, particularly for operational missions, but definitely not for science missions. Now, key point, your performance attributes, all these things depend strongly on your choice of instruments and orbits, depend strongly on the architecture. So if you think about this example, right? We have a constellation, Walker constellation of satellites with visible and infrared images in sun-synchronous orbits, right? So let's say that you focus on one architectural decision, orbit altitude. Probably the most important decision, right? Once you've selected the instrument, orbit altitude is probably the second most important one. How does it affect performance? Well, how does it affect spatial resolution? Well, spatial resolution is directly proportional to orbit altitude in most cases, right? So that's obvious. Revisit time. The higher up you go, the larger the swath for the same field of view. So the better the coverage, the lower the revisit time in general, right? SNR. Well, the SNR is a little bit harder, right? It might be that you go from 400 kilometers to 800 kilometers, and SNR is not hugely, affected, right? It really depends on a number of things for these kinds of sensors. However, if we went to, say, a synthetic aperture radar, huge impact, right, on SNR when you go from 400 kilometers to 800 kilometers, right? Because, with the radar, you have a pulse of a certain power that is transmitted and reflected, right? So there's a, 1 over r to the 4th or over r to the 3, depending on what you're doing, a factor that is going to, significantly affect, right, SNR. Latency, well, that also depends, right? How many ground stations do you have? Where are they? Do you have crosslinks between the satellites or not, right? But generally speaking, it could have, for the same reasons as coverage, it could have an impact on latency. Okay. Now that's the impact on performance, right? Which is what the scientists want. But there's all those other stakeholders, right? And there's, in systems engineering, there's a concept called the systems engineering triangle. I don't know if anybody has heard of that, right? But it's the idea that you have performance, cost, and schedule. It's not just performance, right? You need to deliver a system that meets the performance requirements, but you also need to meet your cost cap, and it needs to be launched on time, right? And then risk, by the way, is in the middle of the systems engineering triangle, because you have risk on performance, risk on cost, you risk having cost overruns, and risk on schedule. You can have your schedule slip by a few months, right, for various reasons. Instruments are not ready. Launch vehicle is not ready, right? You don't have enough plutonium for, for your RTG or whatever, for a deep space mission, right? So lots of reasons can affect risk. Okay. One more thing about cost, it really needs to be a life cycle cost estimate, right? When I teach these to my students and I ask them to do a cost estimate of a mission, they always, think almost exclusively about specific components of a spacecraft bus, like the solar panels, or I'm going to need an onboard computer. Sometimes they even forget that they need an onboard computer, right? I'm going to need reaction wheels, right? So they look up the price of that and add up all those costs, right? That's, if you do that, you're going to underestimate the cost of the mission by at least an order of magnitude, if not 2. especially for CubeSat missions, for which components are relatively affordable, right? Because a lot of the cost of these missions is labor cost, right? Is the cost of the integration, the testing, the development, the science algorithms behind the mission, and so forth. By the way, architectural decisions also have an impact on cost, right? Going back to orbit altitude, your choice of orbit altitude can actually impact how frequently you get eclipses, how long these eclipses are, which is going to drive the sizing of your batteries, right? Which is going to affect cost, for instance. It can have an impact on launch cost, right? It's more expensive to launch to higher altitudes in general. Now, that's somewhat masked by the fact that the pricing strategies of launch service providers do not necessarily take these things into account. A lot of modern launch service providers have flat fees, regardless of where you go in terms of altitude, but that's hiding actual costs. It takes more energy to launch to higher orbits. Instrument cost is another one, right? So if you're designing a radar for 400 kilometers versus 800 kilometers, it's not the same thing, right? You're going to need more power for 800 kilometers, right? So that's going to be more expensive. For propulsion, you're going to have a delta V budget in your mission, right? How much propellant do you need to do station keeping and all these things? That strongly depends on the altitude. At 400 kilometers, you have a lot of drag. At 800 kilometers, you have almost no drag, right? So you're going to need more propellant at 400 kilometers, right? Attitude control system, the same thing, right? If you're lower, you're going to have larger disturbance torques from drag, from other things. You're going to need larger reaction wheels to compensate for those. And there's nonlinear effects also going on here, right? If I need a larger solar panel, now I have a larger moment of inertia, so I need a larger reaction wheel to compensate for that, to control the attitude of that spacecraft, right? And now I have a larger reaction wheel, so that has an impact again on the mass, so on the moments of inertia, right? So it's an iterative process, right? All right, so let me just show you a couple of examples, and then we can close this part. But one of the earlier pieces of work that I did, actually my PhD, was looking at this trade-off. If you have a number of instruments that you chose to fly, do you put them all together or do you have separate missions for that, right? And this is kind of like to illustrate the complexity of these trade-offs. It's not just an engineering thing. Again, it's like cost, schedule, and risk as well, right? So from an engineering perspective, you have the concept of design optimality. If you're designing a mission for one spacecraft, you can really target the spacecraft bus designed to that instrument, right? Now, if you have multiple instruments that go on that same spacecraft, you're going to have to compromise in the design of the spacecraft bus, right? It would have been better to be at this altitude for instrument A. It would have been better to be at this other altitude for instrument B. You end up somewhere in the middle, which is really not good for anyone, but it's the best that you can do in terms of compromise, for instance. Things like electromagnetic compatibility, instruments that operate in the same frequency, maybe one of them is active, the other one is passive, so you have noise from one to the other. Mechanical issues, the vibrations that I was talking about. Field of view issues, everybody wants to be on the nadir phase, so they're fighting for field of view, right? Thermal issues, you have instruments that need to be cryo-cooled, very, very low temperatures so that you can achieve the signal-to-noise ratios that you need, and other instruments, are going to, create thermal noise essentially, right? But then look at all of the green stuff as well, right? If you have dedicated missions, you can have faster time to science. You have lower probability of things getting delayed if you only have one instrument versus 10 instruments, right? All of that affects schedule. You probably also have lower operational risk. There's just less stuff that can go wrong, right? Things like bus cost, launch cost, operations cost. Maybe you could argue that they're lower if you only have one spacecraft. That's debatable, right? Okay, so now we're really getting into what is it that you can do when you're doing this architecting phase of an Earth observing mission in terms of evaluating the mission, right? So there's different methods that you can use. If you're Planet Labs, right, you're a commercial company, your number one metric that should drive every business decision is maximize profit, right? It's all about money, right? So expected profit, or maybe net present value or something like that, right? But it's monetary, it's dollars, right? If you're the government, that's not really an appropriate figure of merit to use, right? And you should really try to think more about value delivered to stakeholders, which again, performance is a good proxy for that, not forgetting about cost and schedule and all these other things, right? So oftentimes we're going to use end-to-end simulation and OSSIs. Anybody know what an OSSI is? Observing System Simulation Experiment. That's a very, very expensive simulation. One of these could, potentially take a week of time that is going to give as an output, say, a weather forecasting accuracy. And you can run it once with the current systems that we have, right? And then that's called a nature run. Then you run it again with the current systems plus whatever mission you're trying to propose, right? So let's say that you have a mission with a LiDAR to measure winds, right? What is the value of these wind measurements with the LiDAR to the weather forecasting community? Well, if I can say that my weather forecasting accuracy to 3 days or to a week improves from 75% to 90%, that's a very good value, right? And that's a very clear, objective way of articulating your value. That's what OSSIs do. Sometimes you can't really do this because it's too computationally expensive, and it would take, if you're comparing, thousands of different designs for the mission, you need something that you can do faster, right? So you go to more subjective things, like just asking experts, what do you think of this configuration versus that configuration? If I give you a ranking, of 1 to 5, is this a 3 or a 4, right? That's based on expert judgment. There's lots of methods related to that, but the units of these assessments are utils, utility, right? How happy does it make you if I have a radar versus a radiometer or both, right? Okay. So I'm going to skip this. There's challenges, of course, related to both the objective side. It takes a long time to do these simulations. And also the subjective side. You can't really tell an expert, okay, I have these 10,000 different architectures. I want you to give me a ranking of 1 to 5 for 10,000 different architectures. They're going to hate you forever, and they're not going to do it, right? So what do we do with these things? So one of the things that, that I've done, and this was actually even in my PhD thesis, I started working on this, we created this tool called VASR, which is basically a rule-based system. A rule-based system is a old AI technology. It's not good for AI. It's basically the state-of-the-art of AI in the 1960s. It was all based on defining if-then rules. If you're in this situation, then do this. And if you have 100 of those, you can recreate relatively complex behaviors. They were good at things like playing chess, for instance, or even medical diagnosis. One of the early successes of these rule-based systems was called Mycin, which was a system to diagnose bacterial infections. It was outperforming doctors at diagnosing bacterial infections because all you need is about 400 to 500 rules to do a good job at that task. But of course, when you generalize to other tasks, that kind of breaks down. But here, the value of that is that these rules are very traceable, right? So I can say, if I have radar and the radiometer in the same band, I can use a spatial disaggregation scheme and generate another data product that is going to have intermediate spatial resolution and the accuracy of the radiometer, for instance. So you can have a lot of these rules. You can specify each requirement also as a rule. You can specify rules that compute the spatial resolution or the temporal resolution of the capabilities. And then basically the idea is comparing the capabilities of a system, the data products, the attributes, with the requirements. That's the idea of this tool called VASR. And the output is, value to stakeholders, right? So you have some inputs that you need to provide. What are the requirements? What are different instruments and so forth? And then you get, these straight spaces here where you have science versus cost, for instance. Each dot there is a different configuration, a different mission architecture. And you can look at trade-offs between science and cost. The nice thing about the rule-based system is that it also generates these explanations. So you can query it, and now with LLMs, large language models, this is seamless. You can do this no problem, right? You can say, okay, why am I getting a score of 0.34 for this architecture? That seems very low. And it will tell you, well, it's because you're missing the requirements on, I don't know, the hydrocarbon monitoring or something. And then you can ask follow-up questions. Well, why am I missing this particular requirement? Oh, it's because you don't have enough spatial resolution. Why do you not have enough spatial resolution? You can keep querying the model, right? These are queryable models that can give you not just numbers, but also explanations for those numbers. That has huge value for the users of these tools. All right, and very quickly, I'm just going to show you an example of tradespace exploration. Tradespace exploration is just this idea of exploring the design space, right? So let's say that I have 5 instruments, for instance, that I'm considering, right? And related to that instrument to spacecraft allocation, right? If I'm systematic, I could have 1 spacecraft with the 5 instruments, or I could have 2 spacecraft with, one with 1 and the other one with 4, or I could do one with 2 and the other one with 3, but there's multiple options there, right? So if you count all of the options and you evaluate them all using simulators, you cost models and things like that, that's what we're talking about, is this tradespace exploration. Okay? So exploring that data set in an interactive way. So you need algorithms to search the trade space. So, optimization is typically used for this. But it's also more the optimization. The final goal of these tools is to provide insight to the user, to help the user make decisions, right? So it's not just optimization, it's also kind of like a data mining side of things here, right? Okay, I get those results, but I want to understand, is the model correct, or is there some limitation in my model that makes the results biased in some way, right? So I have things like sensitivity analysis, association rule mining, and things like that that are important to consider as well. So we've done a lot of work with these interactive feature extraction and knowledge discovery tools. You can highlight those blue area here in the design space and ask the agent to find features, design features that are common among those designs. It looks like those designs, we can't really read this, but they tend to have in common that passive instruments are not found in a dawn-dusk orbit. That makes sense, because if you have a passive, visible, and near-infrared instrument, it cannot be in a dawn-dusk orbit because that's a very low-light orbit, right? So that's not appropriate for that kind of instrument. These instruments, it says separate. So good architectures that are in this area, they never put these instruments together. Why? Because they're all high-energy instruments, right? And they don't go well with one another. You have a LiDAR, a hyperspectral instrument, a SAR. Those are all, they produce a lot of data, they require a lot of power, right? So if you put them together, that creates these economies of scale, right? And you can see that you have, these potentially complicated features that explain the Pareto frontier. If you guys are familiar with that concept, that would be the designs that are non-dominated in the Pareto sense. So for a given cost, they maximize science, right? Or you can just select, I want to be somewhere in this region, right? What do those designs have in common? Okay, I don't know if I can. So this is IFI, this is the data mining tool. So here you can see how you can explore different features that have different levels of explanatory power, basically, of the blue region. You can see here this Venn diagram that's just representing, I guess you just missed the Venn diagram. This Venn diagram right there, the blue region, that's the blue designs. The red regions, those are the designs that have that particular feature that is being, queried. The ones in the middle are the ones that have the feature and are on the blue region, right? Are on the Pareto front or whatever it is that you're trying to see. So there's some trade-offs, I guess, between very general and very specific features that you can explore here. You can also use virtual reality to do some visualization of high-dimensional design spaces. We call this city plot. Every design is kind of like a set of buildings, one building per metric, and you can interactively explore basically this data set. What this allows you to do is give a sense, these are combinatorial spaces, right? So there's no notion of, I guess, continuous design space. They're all binary decisions, right? But this city plot essentially does dimensionality reduction of the design decisions into a two-dimensional continuous space so that distances between two designs are conserved on an average sense compared to the original space. And the z-axis here, the altitude, is proportional to performance, basically. So you can quickly see the sensitivities in the design space. You can use that for one mission. You can also use it for a portfolio of missions. The way the US selects their science missions is through these decadal surveys. Every 10 years, they gather a lot of scientists and ask them about their priority measurements and their priority instruments. And then out of that, they select a number of missions to fly over the next decade. So if you have a certain, budget for those missions and a certain set of objectives provided by the scientific community, you can use something like VASR and tradespace exploration to figure out what is your best bang for the buck, right? What is your best investment to maximize value to stakeholders. And we did a lot of that for the 2007 decadal survey, looking at which instruments to select, which missions to fly, and things like that. Happy to explain some more of that if there's some appetite, I guess. Okay, so I'm just going to show you one more thing and then we'll break. So what's next for designing these complex missions? So one of the things that we've been working on is using these AI agents to support engineers who are designing, exploring design spaces. So just to show you a little bit of a video, this is Daphne. Daphne is a tool that we've developed for 8 years now. So this was way before ChatGPT. We were already working with our own natural language models to improve things. But the idea here, you have this scatter plot. Again, this is science versus cost. Each dot here represents a different mission. And you can, in real time, you have a genetic algorithm that is adding points, adding designs, exploring new designs. The user can hover over those designs, select particular designs, modify them, create new designs. So the GA, the genetic algorithm, and the user are interactively and collaboratively exploring that design space. It also has the data mining side of things, and it also has a question answering system where the user can ask questions about designs in the way that I was talking about. So let's see if I can show some of that. So now the user is doing the data mining. So I think you've seen the data mining capabilities already. And in terms of the Q&A, so this is the user. I'm sure you cannot read this, but it says, what is the most common orbit for an imaging microwave radar? The most common orbit is a low Earth sun-synchronous orbit, right? So it's querying a database, right, in natural language. You can also ask, what do you think of this design? It has a selected design in the design space, and the agent can give pros and cons. This is a multi-agent system, so it can give you perspectives from an analyst, an expert, an engineer, a historian, right? So it can tell you things like, you shouldn't put this instrument in this orbit because it's low light, or whatever, right? It can tell you things like, oh, you put a SAR in GEO. Nobody has ever done this. Are you sure that you know what you're doing, kind of thing? Despite what the model says, there's some uncertainty, right? Or you can also be like, well, nobody has done this, so this is innovative, right? The analyst is using the results of the data mining to provide kind of like suggestions. So it looks like all of the good designs have these in common, so maybe you should consider adding this to this particular design. All right, so that's Daphne. So we've had a lot of research projects recently doing various kinds of Daphne for various things. The latest one is actually probably relevant for Taiwan's industry because it's about designing ICs with chiplets. So if you're trying to design a computer using chiplets, say, I don't know, convolutional chiplets, attention chiplets, GPUs, whatever, it's exploring that design space to minimize energy, minimize runtime, bandwidth, whatever, right? You have different metrics. You can explore that design space interactively with one of these agents. So the first idea to understand of these new systems is that they are what we call agile. So we care about operations because they can actually be operated in a meaningful way. So they're not just looking down all the time like, you know, traditional spacecraft. They can be pointed. Remember what I said about intelligent pointing? So you can do that with these satellites, and therefore we need to make decisions, right? We need to plan where are we going to be pointing at every time, right? So that there's going to be a planning problem, right, for satellites. We could also change the orbit of a spacecraft so that it can see a particular point a little bit faster. Generally speaking, that's not worth, you know, your propellant. At least if you're NASA, that's typically not worth your propellant. If you're other agencies like DoD or things like that, where you have a lot more propellant or whatever, or, you know, if you run out of propellant, you can just launch another satellite, maybe it can be worth it. But generally speaking, we focus on attitude maneuvers. So only changing where we're pointing, not really changing the orbit of the spacecraft. For UAVs, of course, there's a lot to plan, right? You need to decide where to go. You need to do motion planning, right? You also need to plan where to charge or where to refuel, depending on what type of UAV we're talking about, right? Battery-based UAVs, they have limited autonomy, so they have to recharge. So from an optimization perspective, you need to account for recharging in your trajectory planning. For UAVs that are based on fuel, you know, a fixed wing kind of UAV, you also need fuel, and, you know, they have limited range, so you can kind of have to plan, you know, what are the airports in the middle. All right, so I'm going to start, you know, we did a primer on system architecture for the design side of things. Now we're going to do a primer on planning and scheduling algorithms, just so that we have a little bit of the context here. So for Earth observation, we have what we call task planning problems. So there's, generally speaking, there's going to be a set of tasks. So you can think about it from the perspective of just observation task planning. So I don't know, I have a list of 10,000 points to look at, and I have to decide, you know, who is going to look at what and when, right? But also, at least for an individual spacecraft, there's other kinds of tasks, like downlink, you know, when are you going to communicate and how much you're going to downlink, or other maneuvers, such as sometimes you need to point your solar panels to the sun to charge your batteries. Sometimes you need to do momentum dumping. Your reaction wheels get saturated, and you have to do maneuvers to desaturate your reaction wheels. Sometimes you need to point your spacecraft to cold space so that it cools down because it's too hot. So there's other things that you need to task, other things that you need to plan that are not observations. And sometimes you want to consider that. For observation tasks, though, in general, we're going to have a location, which could be a particular latitude, longitude, or a region. We're going to have some kind of time scope. So that could be, you can measure here anytime, or you have to measure here between 3 p.m. and 4 p.m., something like that, right? And we're going to, from a planning optimization perspective, you're going to assign some kind of priority or reward to a task so that you can maximize the total reward, right? That's the idea. So you have the tasks, and then you have one agent, which is a satellite or a UAV, or you have more. You know, you could have a constellation of satellites or a bunch of satellites and a bunch of UAVs, right? Different agents have different sensors and different capabilities. And the idea would be to match tasks to agents, right? You can talk about task to agent allocation, or for a given agent, say for a given spacecraft, if you have a bunch of tasks that have been assigned to you, you can schedule them, meaning you can assign a time to each of those tasks, right? So there's different formulations for these problems, but generally speaking, you know, task allocation, task scheduling are the most common ones. So, okay, I think I mentioned this, but for the single satellite observation problem, you know, there's a single agent, single satellite or single UAV. and you have a certain number of observation opportunities. So typically you pre-compute when you're going to have visibility to each of the tasks. So for each of the tasks, you're going to have a certain number of contact window opportunities. And what you're going to do next is basically select a subset of those contact window opportunities so that, for example, you see each of the points, do each of the tasks at least once, or you maximize the total reward or something like that, right? So there's different formulations. For the UAV problem, instead of deciding on the pointing, right, which is the only thing that we consider typically, it's a little bit richer, so it's more the motion planning, the trajectory planning, but typically you do that based on waypoints, so you're not optimizing like X, Y, Z over time. You're selecting waypoints, and it's more of a permutation kind of problem. Do I go this, do I go here now and there later, or do I do it the other way around, right? It's kind of like optimizing of a space of permutations, typically the way that you do that. So in terms of mathematical optimization, there's two very well-known problems in combinatorial optimization: the 0-1 or integer knapsack problem, which is optimizing over a space of subsets of elements, and the traveling salesman problem, which is optimizing over a space of permutations of elements. So the traveling salesman problem, roughly speaking, is, you have a set of cities and you need to go through each city once, and you have to choose the order in which you're going to visit them without repeating any city or leaving any city out. Okay, so these are the knapsack problem, traveling salesman problem. For the knapsack problem, there's a knapsack, a bag that has a certain capacity, certain maximum weight, for instance, or a certain cost cap, and then there's different elements that add different value and have different weights or different costs, and you want to maximize the total value subject to a weight constraint, right? We're going to talk about some of the limitations of the typical formulations of these problems when you try to apply them to Earth observation, right? But one of the typical ones is going to be these constant parameters. So the reward of a task in a typical knapsack formulation or a traveling salesman formulation would be a constant. However, that doesn't work very well for Earth observation problems for many different reasons. It's because the value of a particular observation depends on the type of sensor, depends on the type of orbit, and the specific position within the orbit, the observation geometry. It also sometimes depends on what other observations are done at the same time, right? So there's kind of like synergies between these data products, these observations, so that you can't just add values, right? When you add values just naively, you can get into missed synergies or redundancy, right? Sometimes you're double counting value for a lot of different things. So you need to be a little bit more sophisticated in terms of your reward function. But generally speaking, the structure, mathematical structure is pretty much this. There's different algorithms that we use to solve these combinatorial optimization problems. The typical one is integer programming, mixed integer programming, mixed integer linear programming. It goes by different names. There's a lot of different tools that are available. Some of them are free. Things like maybe Gurobi. I don't know if anybody here has used Gurobi before. It's a MILP solver, very powerful one. But generally speaking, what you have to do is to put your problem in this form, right? Where you're maximizing some linear function of your variables. If you want to have a linear problem, sum over I and j of xij, vj, where xij would be your variables. Do I assign task j to satellite I or to agent I, yes or no? And vij would be the value of agent I performing task j. Again, it has to be a constant here unless you do something to take care of that, subject to whatever constraints you have, right? So typical constraints are, I want to have at least one observation for each task, right? So covering the set of tasks that you need to do, that's called a covering constraint. And things like, each agent can only do one thing at a time, right? Or if the agent is looking at point A, you cannot be looking at point B, right? So this is kind of like the high-level constraints. When you look at a specific problem, say satellites, you're going to have additional constraints, right? The typical one is slewing torques, right? If you want to look at point A over here, which requires slewing at plus 30 degrees, and 5 seconds later you have to look at point B, which requires you to point at minus 40 degrees. Unless you have huge reaction wheels or thrusters on your spacecraft, you're not going to be able to do that. You're going to have to choose, do I pick A or B, right? So you're going to have to express that slewing constraint. If you want to do it based on maximum torque, which is the reality, that's going to be a quadratic constraint, and that's going to, destroy the linearity of your problem. It's not too bad, but it's slower than pure linear programming. If you give up on the exact quadratic formulation of the slewing constraint, you can have a maximum angular rate, and then you can serve the linear formulation. There can be other constraints that appear there. Sometimes you want to do things like having at least one observation with each sensor type for each task, for example, right? Sometimes you can have other constraints that come from the operation of the spacecraft. So data capacity or energy constraints could be incorporated into that. Integer programming is great. It gives you the exact true global optimum solution. The problem is twofold. One is expressivity. It's sometimes very hard to express problems in a linear way or just in this very explicit way. You need to have pre-computed the VIJs, for instance. If your VIJs are not a constant and they depend on a lot of different things that I mentioned before, it can be hard to pre-compute those. It cannot be computationally feasible. And then the other one is, they can take a really long time, right? So we've done a lot of work with integer programming for relatively small constellations of satellites. As you can imagine, the number of contact opportunities that you get with a certain point, it scales up with the number of satellites and the time that you're looking at, right? So beyond 2 hours or so of planning horizon, if you have something like 5 satellites, it already becomes very slow, potentially impossible to solve these integer problems with, especially with the compute-limited computers that we have on board of spacecraft, right? You can do it on the ground, but you can't really do it on the spacecraft. There's other types of algorithms that we can use. Heuristics are extremely common because they're very fast. Things like greedy algorithms, the Hungarian algorithm for matching. So the idea here is to act locally, right? So I'm going to select the next task that I can see my immediate future that has the highest value kind of thing, right? Very fast, always doable, but suboptimal, right? Meta heuristics are also extremely common, right? Extremely easy to formulate and to use, and sometimes, very high performance, more than we think they're going to give us. The problem is that there's no guarantee, right? You don't really know if the answer is really the global optimum or it could be unlimitedly bad, right? You don't know how bad it is the optimal solution that you're getting or the solution that you're getting. There's other things like dynamic programming. So this is a sequential decision-making kind of problem, right? So at each point, you're deciding what to do next. So you can formulate it as a Markov decision process or a partially observable Markov decision process and use the techniques in that domain like dynamic programming if you have an exact model, transition model, probabilistic model, or reinforcement learning. If you don't have model, you can learn the model, right? But all these methods are based on the idea of learning a value function. What is the value of performing action A in state S? Reinforcement learning, very popular these days for solving this kind of problem, right? And for many other problems, because the performance of deep RL agents has been increasing with the new kinds of models. So we've been working on that ourselves. Here's an example of a little bit of a more sophisticated integer programming formulation. This formulation is good in the sense of being very intuitive, but it's not very efficient. So my primary variables are OTPS. So I'm directly selecting for satellite S at time t, what is my pointing option that I'm using? Am I pointing, I discretize my pointing options and I'm picking one of the, say, 6 pointing options. So that's OTPS, binary variables. As you can see here, everything is indexed by t. That's a red flag in general for computational tractability, right? If you need to If you need to have a variable for every time instant, that's going to not scale very well. There's things that you can do to make this better. ATIPS, this is your astrodynamics right there. This is basically telling me satellite S at time t with pointing option P, can it see ground point I, yes or no? Right, so that's pre-computed using tools like STK, OrbitPy, ORCID, any kind of like coverage analysis kind of thing. RTIPX, this is where we get into the more complicated reward functions. This is basically the reward of performing a task, not a constant anymore, right? In a lot of naive formulations, we assume that that's a constant. Now it depends on time. It depends on the specific ground point, right? It depends on the pointing, right? If you're pointing too off nadir, you may have distortion in your image, for instance, right? Or you may see too much atmosphere that, you can have noise, too much noise in there. And it depends on X, which is the sensor type. Here, YSX is just a mapping between satellites and sensor types. Subject to, the satellite can only point at one pointing option at a certain time, right? It cannot point at, two different positions. And subject to, I can only observe in a place where there's actually a contact window opportunity, right? So that's what is being done there. This right here, this is my torque constraint. It's kind of hard to see, but it says 4i times essentially the delta theta, the difference in pointing angle, divided by the time squared has to be less than a max torque, right? So here we're assuming a bang-bang kind of maneuver, 4i delta theta divided by delta t squared. That's just the torque that you need to perform a bang-bang maneuver of a certain delta theta in a certain delta time kind of thing, right? So you can see how that's not first of all, there's an absolute value there. There's also a square in the denominator, although that's not variable, so that's okay. But lots of different formulations, and again, this is not a very efficient one, it's just a very intuitive one to explain what's going on. All right, so for multi-agent problems, there's a natural extension to this, which is just using combinatorial optimization to solve a task allocation problem. So again, you have n tasks, m agents. What is the best way of allocating or assigning tasks to agents given some kind of reward function, right? So here, generalized assignment problems, transportation problems, there's lots of problems in combinatorial optimization that look at these mappings between two sets of entities, right? Tasks to workers, or moving stuff from factories to inventories, things like that, right? So that's one way of doing the multi-agent task allocation. But there's another completely different class of algorithms for multi-agent problems that is looking at what we call multi-agent coordination. So here we have the agents essentially communicate with one another, exchange information, typically locally, right? So you talk to essentially your neighbors and exchange information about, say, I have observed these events of interest here and there, right? And using that information, you're going to update your, say, reward function and replan, for example, or you're going to, as a group, decide on who's going to look at a given task that has appeared. So there's these two different paradigms. So the typical approach for the second paradigm is either auction-based or consensus-based algorithms, where basically agents are going to bid for the tasks. Okay, so there's an active event, there's a flood or a fire or whatever at this location. One of the agents detects that, tells all the other agents, and then the agents that can perform the task, because they are going to observe that point soon and they have the right sensors for it, they can bid on it. That bid could be proportional to their expected performance to perform the task. And then the consensus has to do with, the group of agents agreeing on who has the highest bid, right? So they have to exchange information oh, okay, it looks like you have the highest bid, so I'm not going to do the task, you go ahead and do it, kind of thing, right? So that's the other class of coordination algorithms. So this table here is kind of showing some of the differences between the typical approaches that, say, operations research people do when solving these kinds of problems, and what we really need in the community for solving planning problems related to intelligent Earth observing systems. First of all, for, say, knapsack problems and, you know, traveling salesman problems and things like that, we typically assume that the tasks are static, right? So you have a list of tasks, and that's what it is, and it never changes, right? So, however, of course, it's very much dynamic in our case, right? As events of interest are detected, we have new tasks that come into play, right? So we have to keep updating that dynamic task. The set of agents is also dynamic. In our 3D chess project, which I'm going to talk about, agents can come and go. They can join the sensor web or leave the sensor web at any time. And they have heterogeneous capabilities, right? So oftentimes we assume in task allocation problems that all the agents are the same. They're all UAVs with cameras. In our problem, the sensors are extremely different, right? You can have sensors, satellites that have radars or optical sensors or, you know, microwave radiometers, right? So heterogeneous agents. And the other one is in the reward function. Sure, we want to maximize total reward, but like I said, in classical OR, reward is a constant. So for assigning a task I to agent J is always worth 3 units of whatever, right? In our case, it's a much more complicated reward function, right? Where, okay, fine, you know, assign task I to sensor J, there's a certain range of performance, but it depends on where in the orbit is agent J. What is the range, for instance, if it's a radar measurement? Or what is my observation angle, my incidence angle, right? So it depends on the observation geometry. It depends on time also. It's not the same if there's an active event of interest. It's not the same to observe it right away versus 6 hours later, where it's perhaps much less interesting, right? So there's a time aspect, an urgency aspect to this as well. And this, you know, for constraints, you know, there's the one agent per task, one task per agent kind of constraint. That's very common. But in our case, actually, we want to be much more sophisticated than that. I already talked about these constraints, vehicle dynamics, max energy, power. But we really, instead of having one observation per task, what we want to really do is to account for the value of repeated observations. So if I look at a certain point once, and now I repeat, you know, do another observation of the same point, the value is not 0, right? It's still adding value, but it's probably also not 1, right? It's probably less value. So you could apply some kind of monotonically decreasing function to the value of repeated observations of the same point, right? That complicates the formulation a little bit more, right? Okay, so this is an example of one of those consensus-based algorithms. So this is called CVBA. So this comes from John Howe's algorithm, John Howe's lab at MIT. So this is a consensus-based bundle allocation algorithm. So instead of assigning one task or planning for one task that comes up, the agents are constantly planning for bundles of tasks. Bundle meaning a set, a sequence of tasks, to make it a little bit more efficient. But roughly speaking, it's a very simple algorithm. So there's a bundle building phase. That's where the agents receive the tasks, and they're going to try to pre-plan for these bundles of tasks. So basically add the incoming task to their current plan. And based on that, they're going to create a bid for that task. So if I incorporate this task into my plan, there's a change in utility of plus 0.3 or whatever. So that's going to be my bid, for instance, right? And then there's the consensus phase. So each of the satellite, UAV or whatever, each of the agents that are going to be able to perform the task are going to exchange bids with one another. So this is literally one number, right? So they don't have to have complicated dialogues about, I have a radar, you have an optical sensor, you know, I'm in this orbit, you're in that orbit, right? That could potentially take a lot of data. So this algorithm is really made for very short amounts of data, which is not necessarily something that is a very active constraint for space. Sometimes for space, you have relatively infrequent contact opportunities, but when you have a contact opportunity, you have a few minutes to talk, right? So you can exchange a lot of data, but that really depends on the orbits and things like that. But either way, the idea is that when you receive the bits from everyone, you update your beliefs about who has the highest bid for a particular task, and then decide on what to do, right? If you have the highest bid, you're going to do the task. If you don't, you're going to release the task and go back to the bundle building phase, right? So that's kind of like the idea. This can happen either synchronously or asynchronously, and you can add a certain number of constraints to make it a little bit more complicated. You can have mutually exclusive kinds of constraints, mutex kinds of constraints. You can have constraints related to these tasks have to be done together. For instance, if you pick task A, you also have to pick task B. That's useful for simultaneous observation kind of requirements and things like that. Okay, so that was the primer on planning and scheduling, and I'm just going to show you a couple of examples now of the value of planning. So when you plan on these autonomous sensor webs in an autonomous way, so no human in the loop, the satellites just talking to one another, how much can that improve the response time? How much can that improve my spatiotemporal sampling? The number of times that I can see a particular event of interest. So this is about that 3D chess project that I was talking about. So the motivation here, this was all in the context of monitoring inland waters. So think rivers, lakes, and reservoirs of fresh water, right? And we're trying to observe these events of interest, which could be extreme storage fluctuations, so floods or high flow events, wetting and drying processes. So these are rivers, we have a lot of those in Texas, that dry out, so the river disappears. And then when it rains, they appear again very fast, and then they dry out, wetting and drying processes, right? Algal blooms, right? When we have this sudden increase in the concentration of chlorophyll in typically lakes and reservoirs. And then ice jams, right? So these are, we have focused really primarily on the first three. But the idea is that we want to be able to detect these events of interest. And whenever we detect one of these, we want to reobserve it as much as possible. And also sometimes co-observe it. So we want different sensor types. We want to observe, say, an algal bloom. It's going to be detected based on chlorophyll A concentration, which is a visible and near-infrared measurement, right? Anytime that we measure the onset of an algal bloom, we also want to measure in that same location water temperature, which is a thermal infrared measurement, and water level, which is an altimetry measurement, or radar altimeter, right? And we want to do that within 6 hours, right? So that's the idea. So this is the goal of 3D chess, was really to mostly perform simulation work to show the feasibility of something like this and to show the value of doing something like this. So this is called, in NASA jargon, to provide proof of concept for this technology. So TRL3, if you're familiar with technology readiness levels, is in the lower end of technology maturity, right? So incorporating this into a flight mission is still several years away, right? We're just doing the simulation work for now. The way that we are going to do this is using a multi-agent simulation. So in Python, we have a simulation where different agents are different threads, which could be run, in different computers if we want it, right? And they exchange information via messages, basically. They can exchange messages by, different mechanisms. It can be broadcasted, it can be peer-to-peer, right? But that's used both for inter-agent communication and also to simulate the observations. So to simulate an observation of the Earth, the agent is going to exchange a message with a special agent, which is, the Earth simulator, right? So 3D chess is really pushing the boundaries of the state of the art. It really looks at agents being much more context aware than what we have now. So they're going to coordinate with one another, reasoning with a lot more information than what we use now. So right now it's all, very static, right? And whenever there's a little bit of coordination, it's based on very specific pieces of information. What we want these agents to be able to do, if we want them to be autonomous, is to be able to reason about not only their own state and their own capabilities, but also about the other agents. What are their states? What are their capabilities? And given different tasks, different types of events of interest, essentially, that come, that appear, being able to reason about who is in the best position to perform these different tasks. And of course, we're going to be dealing with completely heterogeneous agents, multiple dynamic objectives. So it's not just about, measuring soil moisture or whatever, right? We want to measure all these different parameters, right? And we want to do that in a decentralized way in order to avoid the bottleneck of centralized planning, which can be very computationally expensive. Okay, so here's what the ConOps looks like. Imagine that you have one of these sensor webs, okay? So we have different types of agents. We have satellites, we have UAVs. Everybody has different sensors, and some of these agents have onboard data processing capabilities. So they have algorithms on board to get the raw data and perform a rough, they don't have to do the real thing, right? The whole data processing pipeline. They can process the raw data and look at outliers, for instance. Detect that, the value of water level in this point is 2 sigma above the historical values for this time of the year in this particular reservoir, right? That generates an event of interest, which is going to generate a task request. That's the idea. So the agents that generate a task request are going to communicate with the network, propagate that information throughout the network so that over time, more and more agents, potentially not everyone, because we don't have a guarantee that the network is fully connected, right? But at least locally, you're going to get that information propagated. And then the idea is that we're going to also share some information, not just about the event of interest, but also the severity score and what is the expected duration of that event. So we call that the characterization of the event. So all that information is going to go into the task request. So the task request is going to be, I need someone to measure water level and water temperature at a certain latitude, longitude, with a certain spatial resolution within 6 hours, for instance, right? And the severity of these is a 7 out of 10. So now the nodes that receive this information are going to reason. Again, this is when the context awareness comes into place, right? So they're going to use a very large knowledge graph, a very large knowledge base to reason about all of these capabilities. So what is the mission at hand to measure water level, measure water temperature, and so forth? What are my capabilities, right? Well, I have a thermal infrared sensor, for instance. Can I perform the mission, yes or no, right? So the idea is that using reasoning over these knowledge graphs, using embedding-based methods, for instance, combined with logical rules, you can basically do soft matching. So, okay, so I don't have a sensor that is labeled as measuring water temperature. So I don't know that I can measure water temperature, but I know that I have a thermal infrared sensor. And based on the knowledge graph that I have, I can reason my way through, because I know that this knowledge graph has a lot of information about types of sensors, parameters that people can measure, other agents that have thermal infrared sensors can measure water temperature. So I can infer a certainty value. It seems like it's pretty likely that if I measure here, it's going to be a useful measurement for water temperature, right? So that's the idea of this reasoning step. Oops. So you can kind of see here what that looks like. So there's a task request that wants to measure water temperature. I have triples, as it's called in my knowledge base, that say that water temperature can be inferred from thermal infrared radiance. And I know that I can measure thermal infrared radiance. Therefore, I'm going to infer that I can perform this task. All right, so now there's a subset of agents that know that they can perform the task or think that they can perform the task. So those agents are going to enter this decentralized planning phase, where they're going to decide on who is going to do the task, basically, right? Based on the consensus-based algorithm, for example, right? And actually, we're going to see two different ways that they can do that. But either way, there's going to be a bid, which is going to be based on this utility function that is going to incorporate a science value function that is going to actually use something very similar to Vassar. So it's going to use a performance calculation, different attributes, spatial resolution, spectral resolution, and so forth, combine all of that into how well you can meet the requirements of the task and come up with an S here. And then there's, of course, the cost, right? So different agents may have a different cost to perform a task. So that may be more important for UAVs than for satellites, although even for satellites, there's, I guess, a cost to slew, right? And there's also an opportunity cost, right? If I measure task A, and there was another task B over there that I could have measured, and now I can't measure, there's an opportunity cost for that you can incorporate, right? So now, you know, we have decided who's going to do the task. Everybody updates their plans and continues, right? And this is very dynamic. Agents can go on and off. Tasks, you know, continue to appear and so forth, right? Okay, so I don't know how I'm doing in terms of time. Okay, we have a few minutes still. But what I want to do now is just show those examples. Like I said, we built a multi-agent simulation. You can kind of see here there's different types of agents. There's satellites, there's ground stations, there's also UAVs. And then there's this environment server. So that's a special kind of agent that provides the simulated observations to the agent. So a satellite that is observing a certain lake is going to say, I'm observing, you know, this lake right now, and the environment server is going to say, okay, so here's the radiance that you're observing, for instance. So if you want details, you know, there's a paper. I'm not going to go too much into the detail, but each agent has different threats to simulate different parts. There's a science module. This is what runs the onboard data processing algorithms, you know, the detection of the algal blooms or the different events of interest. The engineering module is kind of like what simulates the spacecraft, what simulates the different subsystems, the batteries, the onboard computer, the communications. And the planning module is what does all that reasoning and what schedules the different tasks, right? So it's kind of like the flight software in a sense. I'm going to skip this. This is the knowledge graph. So we built this by taking a lot of information from a database that is publicly available. It's called CEOS, Committee on Earth Observing Satellites. It contains information about both current missions and planned missions. What are their sensors? What are the data products? So we got all of that from the web, put it in a big knowledge graph. And then we also complemented it with additional information that we mined from this journal, the IEEE Transactions on Geoscience and Remote Sensing, which is a very well-known remote sensing journal. So we took all of the papers from 1990 to 2020 and mined for information triples is what it's called for knowledge graph. So that's, you know, entity, relation, entity. For instance, L-band radiometer can measure soil moisture, right? Entity, relation, entity. We were particularly interested in two types of triples for that. One is instrument type measures observable geophysical parameter, and the other one is geophysical parameter can be obtained from data product. So like water temperature can be obtained from thermal infrared radiances, for instance, right? So the problem is that in this knowledge graph, you know, there's two very different kinds of triples. One is what comes from CEOS, those are true for sure, right? There's no uncertainty about whether Landsat has a certain type of instrument or not. Landsat has the instruments that it has, right? However, if I have natural language processing algorithms extract information from papers, there's a lot of uncertainty about that being fully correct, right? So what we do is that we augment the knowledge graph with a confidence factor for each of the triples from 0 to 1, with 1 being certainly true, 0 being certainly false, and basically create what is called an uncertain knowledge graph. and then used algorithms that are designed to reason over these uncertain knowledge graphs. I'm not going to go into the details. I don't know if the slides are going to be distributed or not to the students, but there's some details here about the algorithms that we use to reason over these different types of knowledge graphs. Happy to share more information later if people are interested. But basically, we use Uniker when we don't have the confidence factors. That combines embeddings with logical rules. So the idea of embeddings is basically assigning low-dimensional vector, say in R, 512, for instance. So a real vector of numbers of dimension 512 to each entity and each relation. So you learn this hidden space so that then you can reason about relations that are missing from your knowledge graph. Okay, so I don't really know that I can measure water temperature with this type of sensor, but what is the probability that I can measure that, right? Based on the structure of the knowledge graph. So you can do these kinds of reasoning. Okay, that's Uniker. I'm going to skip through that. And then UKGE, so that's an embedding algorithm for knowledge graphs that are uncertain, right? So here, it's a completely different problem, right? Because instead of trying to infer what is the probability of a certain missing triple being true, now it's a little bit more complicated. You kind of have to regress the confidence factor between 0 and 1. It's not a classification problem anymore. It's a regression problem. You want to basically figure out what is, or estimate what is the confidence factor of a triple that is missing in the knowledge graph, right? So you can do that, by basically finding the embeddings that minimize this mean square error between the actual confidence factors and the predicted confidence factors, right? You can also add this other term here that if you have logical rules, you can minimize the distance to satisfaction of these logical rules for the unobserved triples. Right now, this works decently well. So the mean square error is about 0.04. So if you do the square root of that, that's 0.2. So this means that in general, if the knowledge graph or the reasoning algorithm thinks that something is true at 0.6, it could be 0.4 or 0.8 roughly, right? So it's not very good it's not very precise, but to drive operations, which is what we're trying to do here, it's probably enough. Okay, so we've done a lot of this decentralized coordination benchmarking. So we tried lots of different cases. What happens if event duration is 6 hours versus 2 hours versus 12 hours? What happens if instrument field of view is 5 degrees versus 10 degrees versus 15 degrees? And we benchmarked these two main approaches. This periodic sharing of information and replanning. So this is when periodically, say every 10 minutes, agents exchange information about their observations. I have observed here, here, and here, and there was an event here, but no event here, for instance. And then based on that, they're going to update the reward grid, basically, for the different points, and replan. So very simple. And then the other one is the consensus-based decentralized task allocation, right? So I don't wait. This one doesn't really wait for the next, planning horizon. At any point, if there's an event of interest, it generates a task request, and it performs, uses CBVA to figure out who's going to do the task, right, immediately. So these two are not really mutually exclusive, but that's really what we have done so far, is to treat them as mutually exclusive things. But they could totally be combined, right? I mean, you could do this, and then in between planning cycles, you could do this, right? Okay, so I'm going to skip this. This is how we compute the value of a task. There's all this framework using Vassar basically to compute the value of a task, taking into account the performance attributes. We call these, or I call these, executable science traceability matrices. So I don't know if you guys are familiar with science traceability matrices. Is a very common tool used in the planning of Earth science missions that has, like, for this mission, these are the science objectives, these are the measurement requirements, instrument requirements. So this is essentially an executable science traceability matrix that takes into account all of these requirements and computes in real time the satisfaction of these requirements. I'm going to skip this. Okay, I'm going straight into the examples. All right, so this is a case where it's very simple. We call this the rainfall case. So what we want to do is use information provided by a satellite that can measure precipitation. It's called GPM, the GPM satellite, and basically try to observe more whenever there's a rain event. So that's very simple, right? So this is useful for both floods and algal blooms because both of those have a obvious dependency on rain. If it rains, it's going to flood, right? But also if it rains, it can affect algal blooms as well. So we have this constellation of satellites, 36 satellites, 6 by 6, at a tropical kind of inclination, 45 degrees, 700 kilometers, 60 degrees field of regard, right? But actually very small field of view, right? It changes depending on the case, but this is like a Landsat kind of field of view, but you can do the agile pointing. So what we found in this particular case, and I don't know if you're, no, not in this one. Well, what we found in this particular case is that we go from observing 5 of these points that have rain with Landsat to 52 with the constellation that doesn't do the coordination. It does do initial planning. So that means that the satellites have a list of all of the points that have rivers or lakes or points of interest. And it's going to plan to observe all of them if it can, right? And when you have the coordination, the replanning, you get up to 1,600 events out of 5,000 possible, right? So that's a very significant increase. So now, if I want to not only re-observe the event, but co-observe it from different sensor types, so now I will have radar altimeters, visible and near-infrared sensors, and thermal infrared imagers. So upon detection of a rain event, I want to measure with all of those, basically, because I want to know water quality, which requires the visible and near-infrared. I want to know water level, quantity, which requires the altimeter. I want to know water temperature, which requires the thermal infrared, right? So here, if you don't do coordination, you get zero co-observations, right? None. If you do the the coordination, you can see 13. Now, this is not a lot, 13, right? But just based on astrodynamics, this is a very constrained problem, right? So there's actually in total only 355 potential opportunities for co-observation. Oh, you can kind of see here, I guess it was an animation. No? So you can kind of see the satellites, and if you're not colorblind like I am, you can see the points kind of like changing color, right? So they're changing color as you have these co-observations, right? So what you want is to have this color, which represents a co-observation, right, as much as you can. Okay. So now, after these rainfall kind of scenarios, we did a systematic study where we, basically it's a little bit more abstract, but we consider different levels of satellite agility, event duration, event quantity, whether the events are clustered or they happen uniformly around the world, field of regard, field of view, constellation design, and the number of types of sensors that are needed for the co-observations. And we looked at, for all these different cases, there's a lot of them, right? And we couldn't really do them all, so we did a design of experiments kind of thing where we looked at 49 of those. What is the value of the replanning? What is the value of the coordination? So this is the details of how we did the reward of repeated observations. You can look into that if you're interested. This is the details of the algorithms that we used. So this was a dynamic programming algorithm that we used for the basic planning. And here's the main result, right? So basically what happens is that coordination almost always helps, but the extent to which it helps, the value of coordination is highly dependent on the specific characteristics of both your constellation and your events. So So what is it that drives, do you have, are you here where the value is pretty small, or are you over here where the value is pretty large, right? So we did a follow-up thing where we did a sensitivity analysis. So we looked at what is the most important parameter that drives the differences that we see. And we saw that event duration was probably the most important factor, right? And this is somewhat unintuitive, right? Because you might think that if the event duration is very short, that the value of coordination would be very large. But what happens is that if the event duration is too short, then sure, you can try to coordinate, but there might not be any opportunities really to reobserve just based on astrodynamics, right? So what happens is that a medium event duration is kind of like the sweet spot, basically, for the value of coordination in this case. You can kind of see here, and this doesn't go beyond 6 hours, but if you go beyond 6 hours, we've done some cases, and for events that are too long, then you don't really need coordination either that much, because just by pure chance, you're going to eventually reobserve everything, right? Let's skip this one. We looked at the CBVA versus periodic sharing. I'm not going to go into the details, but there's something interesting. There's some trade-off basically between exploration and exploitation that happens with this CBVA. So what happens is that if a satellite decides to respond to a task request, right, it's essentially missing an opportunity to observe other points where it could have detected other events, right? So if you have a lot of events, that could be noticeable, and it could lead to basically a trade-off between detecting new events versus reobserving known events, if that makes sense. So that's something that we saw here. I'm going to skip this, but I already mentioned that we looked at, one of the program managers at NASA was asking, centralized versus decentralized planning. Do we really need decentralized planning? And the answer is yes, because the centralized, the integer programming algorithm breaks down beyond a certain number, a certain planning horizon, which appears to be about 1 to 2 hours. That's heavily dependent on the formulation that we use and things like that, but it's challenging. All right. This is just a little bit of next steps. So there's certainly more coordination strategies that we could have used that are not just based on optimization or not just based on these consensus-based algorithms. We could use the knowledge graph reasoning much more, and actually you can do a very decent job if each agent just reasons about the capabilities of the other agents and essentially propagates the orbit of the other agents, and unilaterally, without talking to anyone, determines who is in the best position to perform the task. So essentially, each agent could solve the global problem, essentially, right? And decide, it would have to be probably with heuristics, because you can't really solve the global problem on board, but all of this to say that you could use the KG a lot more for the coordination side of things. And then another big thing is that so far we've only been doing detection of events of interest and reacting to events that have already been detected, right? But if you have predictive models, and we have demonstrated this with a predictive model that we have of river flow, you can actually react to events before they occur. And that's when you really get into improved response times, right? If you can basically plan to observe a point before an event, a flood, a fire, whatever is actually detected, right? Because there's a model that has predicted that there might be an event there at a certain point in time, right? So these predictive models, we have a team at UCLA working on decentralized Kalman filter that we can use to help with this. And then the other thing that we have not done is actually model any kind of communications, imperfect communications aspects, right? So far, we've been focusing on the ideal case where you have line of sight among all agents and infinite bandwidth, zero latency, right? But as you start incorporating realistic constraints for communications, you create an information asymmetry between the agents, right? So they know different things, because information has not fully propagated yet. So that basically leads to suboptimality, right? And the extent of the suboptimality depends on how bad, the latency is, for instance, right? The other thing that we want to do next is go to the next step of the development, which is demonstrating this with hardware in the loop, right? So we have a small motion capture system in my lab with quadcopters, and we're trying to run these algorithms in real time on these small quadcopters to demonstrate, the coordination between the different UAVs to observe a point on the surface. So with that, that's the end of my presentation, and I will take any questions.